In section 242, we're going to see another application of how we can use integrals to compute something completely different than areas under a curve. Now, in the last section, we took a look at how we could use an integral to compute the length of some curve. And we're going to use a lot of the same sorts of ideas in this section where we try to find areas for a surface of revolution. So we're going to be back to taking curves and spinning them around an axis to generate some sort of a 3D solid. If you take a look at what I have here, though, at the beginning, we'll see that I'm not going to be rotating an entire region around an axis, but rather here just this outer boundary curve. And when I do this, I'll kind of create the shell of a solid as opposed to something that's solid all the way through. And our goal is going to be to find the surface area of this solid, or you can roughly think about it as how much paint would I need in order to be able to paint the outside of this figure? Like, what's the square footage that I would need to be able to cover? And so you can see here that different curves that I go ahead and I spin around an axis will create different sorts of shapes. If I kind of spin this half circle around an axis, I create a sphere shell. And if I spin a horizontal line, I create kind of like a cylinder. If it's a slanted line, I kind of get this, well, almost like a part of a cone type shape. And if I spin some crazy curve, I can create a lot of different sorts of strange shapes. And so the question is, again, how do I find the surface area of one of these shapes? So let's take a look down here to see how we might actually go about doing this. So I'm going to suppose that we're going to be spinning a curve C around an axis. We'll state here, or use the x-axis, and we want to find the surface area of the resulting solid. Now I'm going to start here by making a really big assumption about our function that is going to be helping to give us our curve C. So I'll start by saying that let's suppose f of x is a non-negative function with a continuous first derivative. So much like what we saw in the last section, I'm starting here with some really strange assumptions. F's got to be a non-negative function, and it's got to have a continuous first derivative. But why am I making these assumptions? Well, you'll see as we continue to move through this question, or this derivation here, why exactly these points become important. Now, we'll also go ahead here and start by saying that let's suppose C is formed by the curve y equals f of x on an interval from a to b. So I'm going to go ahead and draw a picture down here, okay, just to kind of illustrate what it is that we're working with. So again, let's just suppose that I have some value of a, some value of b. I'll kind of draw a picture similar to what we did in the last section, right? So maybe here's going to be a function y equals f of x, but it's only drawn on this interval, and so that creates the curve C. Now again, if I'm going to go ahead and take this curve and attempt to revolve it around the x-axis to make a solid, I want to go ahead and start to figure out a way I might be able to at least approximate the surface area. And so what we're going to do is something very similar to what we've always done in all of these different sections. We'll start by taking our interval from a to b and chopping it up into a bunch of smaller subintervals. So I'll state over here that we will divide a to b into n equally spaced subintervals. That's what we're going to be going ahead and doing. And so you can see over here I've created, I don't know, it looks like 5 maybe total intervals. And we're going to take, again, another similar approach to what we did in the last section, is that we're going to go ahead and at each one of these individual x values, where we now have an end of an interval, we're going to go up and put a red dot up here on our function. And also, like we did in the last section, we're going to play a game of connect the dots. That is, we're going to go ahead and draw a straight line segment that connects each one of these red dots to the next dot. Okay, and so again, we saw in the last section that we used these line segments to approximate the length of the curve, but we'll also see here that we can use them to approximate the surface area of the resulting revolved solid. Now again, I'll go ahead and just record down what we've done over here in words. So we'll say at the endpoints of each interval, we will place a point on the function. So that accounts for our red dots. And we will then connect these endpoints, or I'll just say connect these points with line segments. So what we're going to be interested in taking a look at now is how do I use these line segments to give me a rough approximated surface area? Well, if we take a look at the next page, we can kind of see how we're going to do this. You'll see down here I have a similar sort of a picture sketched out where I have these different dots sketched along a curve that kind of represent these different red line segments. But you can also see that I've rotated them around, and when I rotate these segments around the x-axis, I kind of create these individual bands, if you will, that when stacked all up, give me a rough approximation of the full 3D surface. So I'll start by saying, or kind of repeating that up here, say that revolving each segment around the x-axis creates a band each of which has a surface area which is roughly equal to the surface area of the solid on the same interval. So I can see that each one of these again provides me maybe a rough approximation. But how do I find the surface area of one of these bands? Well, specifically here, I'll be able to state that each band is a portion of what we would call a right circular cone. You can kind of see here that if I was to imagine looking at one of these bands, maybe like in the second picture here, if I was to continue to extend out these edges that I have, eventually they would meet up and they would come to a point, and I would have the shape of a cone. So these shapes are kind of created from taking a cone and kind of lopping off the top side of that cone. And these shapes actually have a special name. These bands, or portions of the right circular cone, are called frustum. Right? So this here is a picture of what we would call a frustum. Now it's possible you may have heard of a figure like this before, or maybe not. Maybe this is the first time you've ever heard of it. But it's actually really easy to go ahead and find the surface area for a frustum. I'm not going to go through the full details here, but again, since you can see that this sort of a figure comes from this cone-like shape, if I knew how to find the surface area for a cone, which is a rather simple thing to find, and then I could kind of just subtract the surface area for this kind of upper cone part up here, then I would be left with the surface area of this kind of lower bottom half. And the surface area for this is actually going to be given by the following. The surface area for one of these frustum is given by pi times the quantity R1 plus R2, and then times L. And you'll see here that the R1, R2 kind of stands for the radii of these different size circles that exist on either end, and L represents the length of this kind of slant height, or, if you will, it's also the length of our corresponding line segment that got revolved around. So this is kind of a weird formula that we're going to have to use to try to go ahead and then approximate the total surface area of the resulting solid. So you can see here that I've zoomed in on another picture of just one of these individual frustum, and you can see that I've kind of labeled here the interval that I've started with. Okay, I've gone from some x sub k minus 1 to x sub k. I have a delta x width then for that interval. I can kind of see over here where I'm going to have my y values on my function, and my individual line segment that I had would be positioned right up here. This is what's getting revolved around. And so the y value over here, of course, is found by taking this x and plugging it into the function. The y value over here, take my x sub k and plug it into the function. So I'd like to go ahead and try to use this then to try to set up the formula for the surface area for one of these frustums. So I'll start by saying this. I'll say the kth frustum has radii of, well, let's see, the radii are going to be the radius of these two different circles that I have here. And if I look at this picture, I can spot that those radii for the circle that's listed here is actually just going to be given by the distance from my x-axis up to this point, which is, of course, exactly this y value. So there's a radii here of f xk minus 1, that's my small radius, and my big radius occurs on the other side with a distance of f of x sub k. Now, the slant height, that is the length of my blue line segment up there, is also super easy to find. So here we have a slant height of, and this slant height should be super easy to find because, again, we can use the idea of Pythagorean theorem that we talked about in the last section. And you might remember that we had a giant radical in the last section that we used. Notice that we would have something like a delta x squared. That's the length of this side down here. I would have to add to that the length of the other side, which is found by doing my x sub k minus my f of x sub k minus 1. And if I square that, now I know that would be equal to the length of the hypotenuse squared. And so when I square root, I just get the length of that hypotenuse. So with all of this then in mind, it becomes easy to find an easy approximation for the overall surface area. I know then that S sub k, that is the surface area for the kth frustum, would have to be given by pi times f of x sub k minus 1 plus f of x sub k, and then times this giant radical, which again has this delta x being squared, and my f of x sub k minus my f of x sub k minus 1, all squared. So this is a formula for the surface area of the kth frustum. And therefore, it would not be very surprising to go ahead and see that we could say that the surface area for the whole figure, we would estimate or find it very reasonable to believe that if I let the number of bands that I use approach an infinite number, starting again at band number 1 and going to band number n, if I was to take the limit of the sum of all of my s sub k's, then this would give me the surface area overall. So of course, I can imagine then that if I can see this here as hopefully a definite integral, or if it has the shape of a definite integral, then I'll have an easy way to ultimately compute my surface area. But as I write this down, as I kind of fill in this formula for my s sub k, I can start to ask, does this actually look like the general structure or the general form for a definite integral. Remember again what every definite integral had in it. It had a limit, which we definitely have here, and it had a sum, which we have here. It also had a special function with a special x plugged in, and times delta x all at the back. And unfortunately, much like what we saw in the last section, we don't really have that yet. Over here, we kind of have this big, ugly mess. We have a really complicated looking thing with different x's being plugged in, and it's not even times delta x. Again, delta x is kind of buried deep within the center of all of this. So how do I go ahead and begin to maybe attempt to rewrite this so it looks more like a definite integral? Well, of course, I might be able to go back and pull on the ideas that we used last time, specifically the mean value theorem. So what we can write is this. Now, by the mean value theorem, I'll use the standard abbreviation. Remember that we know that we can apply the mean value theorem because we know that our function f is going to be differentiable on the interval from a to b, and it'll be continuous on the interval from a to b. And remember, that was the reason why we needed this second green condition over here. This is really important for us. So again, this is crucial to have to make the mean value theorem work. But by the mean value theorem, we know there exists a value, we'll call it xk star, and it exists in the interval from xk minus 1 up to x sub k. Remember, that's going to be in the picture, that is, there's some special x that exists in here. Xk star is somewhere in here in the picture. And the goal of this is to say that somewhere along the curve, remember that the curve of the function is actually, maybe looking something like this, and then my line segment is approximating the length. But there's got to be some point on there where there's a slope of a tangent line that's equivalent to the slope of that blue line. And so we can go ahead and summarize that by stating that there is a value in this interval, again, such that I know that the derivative at my xk star, that is the slope of that tangent line, is going to be equal to the slope of my secant line. That is the line that connects those two endpoints. Now, also keep in mind that we said in the last section that this distance down here is just delta x. That's the length of my interval. And so if I multiply this over to the other side, what we'll see is that what this gives us is that f prime of xk star times delta x is ultimately going to be equal to f sub k, or f of x sub k, minus f of x sub k minus 1. And this was particularly useful because it would allow us to transform this radical that we have up here. So similar again to the last section, we can see that our pi of f of x k minus 1 plus f of x sub k times our giant radical, write that out carefully here. So this is the radical that we used to have, but now with this update, you might recall that I can simplify my radical down very rapidly. And I'm going to leave out a lot of the detail here because I'm assuming you can go back and watch the section on arc length to go ahead and see how we simplified this before. Oops, sorry, I forgot my plus sign in here. Those should be added. But remember that I can simplify this ultimately all the way down to just get the following. When I do my substitution, there will be a delta x squared that's in common. I can factor the delta x squared from under the radical. I can then square root each of the individual pieces, and I'm left with something like this. Notice that now this is an improvement over where we have been previously. We want what we have up here to be a definite integral, and it's not there yet. But with this manipulation, we now have at least a whole bunch of stuff times a delta x. We're closer. But what we still don't have is a single special x that's being plugged in. In fact, at the moment, what we really have is 3 different x's being plugged in. And so we'll come up with one final way that we might be able to simplify this down. So I'll go ahead and on the bottom of this page, I'll make one additional note. So I'll even state, we note that as n increases, that is, as the number of bands begins to increase, delta x will become smaller. Right? I mean, if I have to have more bands, then each band has to have less width or less thickness to it. Those starting intervals have to be smaller. And if that's the case, let me recap. So I say we note that as n increases, delta x will become smaller, and since f of x is continuous on our interval from a to b, then we can definitely state that when this as this interval begins to shrink, I'll notice that this xk star that we found that's kind of wedged between these two endpoints is going to actually become closer and closer and closer to being the same x value as our endpoints. Just imagine having this interval shrink down. If this xk moved a little bit to the left, and my xk minus 1 moved a little bit to the right because my interval is shrinking, then my endpoints are going to be even closer to my xk star. And so since my function here is continuous, meaning that it increases and decreases at a consistent sort of a rate, or at least there's no large jumps or changes in the y values of this graph, I can state that my f of x sub k minus 1 should almost be the same as my f of xk star. Again, you can even go back and take a look at this in the picture. The y value over here is very close to the y value over there, and as I shrink the interval down, they're going to be even closer. So I have that these two values are almost the same, but I can also make the claim that f of xk is almost going to be the same as f of xk star. And so another way that I could update what I have up above is to state this. I could say, so it becomes reasonable to approximate the surface area of a frustum as, and notice here I'm just going to pull out my s sub k, which again is exactly what we had up here, but notice now that instead of writing my f of x sub k minus 1 plus my f of xk, I'm going to swap those out for what they're almost roughly the same as, which is my f of xk star. And if I write this down, what I'll see is now I only have a single x that's actually being included in this big, complicated surface area approximation. And so I could simplify this down just a tiny bit more. I'll notice if I have one of these f of xk stars plus another, I really have two of them. And so I'm going to just go ahead and choose to write it in the following way. I'll just write 2 pi f of xk star, then times 1 plus the function's derivative squared and delta x. But of course, what this gives me is that the surface area now should be given by a limit as n approaches infinity, where I'm going to have start at frustum number 1 and go to frustum number n and add up these surface areas. And so if this is a formula then for the surface area, I can now see that this does meet the conditions to actually be a definite integral. Notice again I have a times delta x at the back, and the rest of this kind of operates as one large messy function with only one single special x plugged in. And so I can go ahead and rewrite this then as an integral from a to b of 2 pi f of x times the square root of a 1 plus an f prime of x all squared dx. And this is a definite integral that represents the surface area of the resulting solid.